Hi guys, I want to go over some things about something called phase shifts. Earlier this week, we posted some material in the notes involving the position time graphs, velocity time graphs, and acceleration time graphs for objects in SHM. So here back in our notes was a position time graph function, A representing amplitude cosine of omega angular frequency times time t plus the phase angle phi. We're going to show how this could be written as a sine function as well by changing the phase angle. This is going to be the most important thing to do today. And in a similar fashion, the velocity time function, which in the notes is shown with the sine function, can be written as a cosine function with the proper phase shift, meaning different phase angle, and the acceleration function, which is shown in the notes as a cosine function, could be written as a sine function. Because it turns out sine and cosine functions are really just small variations of the same function. So I'm going to use Desmos to help us here. I'm mainly going to deal with the position time functions, but I will point this out on the other functions. It's all the same idea. The biggest thing is understanding generally how cosine and sine functions are really practically the same thing, just shifted by phase, meaning a horizontal right or left shift. So what we could see here is I have up right now showing in blue the most basic cosine function possible. All right. So y equals cosine x. On Desmos, it doesn't let me make the x variable t like it's shown in our notes. So we just have to imagine here that the independent variable t in our actual equation is going to be represented by x on Desmos. Okay. So most basic cosine function is y equals cosine x. So that would show us a graph that looks like this. And the reason why for SHM situations we use sine and cosine functions is because the functions mathematically oscillate just like the object in SHM does. So it's a perfect mathematical function to show back and forth motion. All right, now I'm also going to click up over top of this one, the most basic sine function, which would be y equals sine of x. And it's going to be in red. We could see that those two functions on top of each other look almost identical. They have what we would call the same amplitude. They both go to a maximum vertical height of 1 and a minimum of -1. We could also see that horizontally, other than the fact that they look shifted from one another, it looks like they stay the same distance apart, or in other words, have the same frequency horizontally. Just one is shifted over compared to the other. That's what we call really a phase shift. So what I'm going to simply do here is turn a cosine function into a sine function by simply changing the phase angle. So let's take a look at the probably the most notable features of a cosine or sine graph, and that would be the high points. In wave terminology, we call the high points crests. So I'm going to refer to them as that. So let's look at the crests of each one of these patterns, particularly right here on the cosine function and right here on the sine function. I want to turn this cosine function into this identical sine function. So you could imagine that to do that, I would have to shift this crest right here at an amplitude of 1, keep it that same amplitude, and if I could drag the whole graph to here, they would be identical functions, right? And notice here, horizontally, x value is pi over 2. So I basically need to shift this by pi over 2. Now, it turns out with phase shifting, to shift to the right, we need to subtract that value, pi over 2, off of the x value within the quantity of the function. And Desmos does not allow me to easily plug in pi, so we're going to have to go decimal form. We can see on the graph pi over 2. Pi over the 2 is the equivalent in radians is 3.14 over 2, which is 1.57. So I'm going to click on the graph of the cosine function with a phase shift of minus 1.57. Remember, 1.57 in radians really means pi over 2. So if I do that in a moment here, what I should see is I get a shifted graph. So I'm going to unclick the basic cosine function that we had. And I'm going to turn on, actually, excuse me 1 second. I need to change something from above here. I have another graph, it looks like turned on above that I want to turn off. We'll get to that in a second. Oh, there we go. Let me take it away. Okay, so now I'm just showing the sine function, but now I'm going to click on this cosine function. And notice what happened. I'm going to click and unclick it. It overlaps it. It's the same function. That's what we call a phase shift. So what you may see throughout this chapter when dealing with position time functions, velocity time functions, and acceleration time functions of objects in SHM is that sometimes maybe a problem in a book will give a position time function written with the sine function. And you might say, wait a second, we were told in our notes that it's a cosine function. The point is, you could write it either way with the proper phase shift. A phase shift of 0, oops, wrong graph. A phase shift of 0 means that that particular function starts out from 0. Phase shifted, it's like you slid it to the right or slid it to the left. So this blue function right now is a cosine function, but it's not a basic cosine function with a phase shift of 0. That was this one, okay? When we put a minus pi over 2, or the equivalent of 1.57, it took it to the right that amount and made it overlap the sine function. Let me bring both the basic cosine and sine up again. I could phase shift, I could do it oppositely. What if I want to turn the sine function into a cosine function? Then I could simply take that sine function and you would imagine sliding it from here to the left, correct? By pi over 2. Now, if I want to slide to the left, I add 1.57 or pi over 2 to that quantity. And you can see now that overlaps with the cosine function, the basic cosine function. So when we add or subtract values within the parentheses to the independent variable x or t specifically in our formulas, that's basically just like grabbing the functions and moving them right to left. So with that in mind, let's go look at a function that looks a little more like what we have going on in our position time function. Remember, I can't make xt, so we're going to imagine that x is a t. That's going to be our omega, which is angular frequency. P is going to represent phi, the phase shift, and A is amplitude. So let me just vary some of those. So if we only change the A value, we change the amplitude of the function in black we're looking at. I left the general cosine, most basic cosine function in blue in the background just as a comparison. So as I vary A, the amplitude, you can see it changes nothing but the vertical arrangement of the crests and troughs. Everything else about the graph stays the same. So that just changes only the amplitude as defined. So if we set the amplitude as 1, then it matches right now the basic cosine function. Now, if I change omega, what's in front of the independent variable within the parentheses, that's what's going to condense it horizontally or stretch it horizontally. So let me vary that some. You can see as I make omega lower, that stretches out the function. That would affect the time period as well. That means whatever object is in SHM now as compared to before is basically not bouncing up and down as quickly. But if I increase omega higher, it condenses everything. Now the time period is going more quickly. So this object that might be something on a string bouncing up and down or side to side on a spring, or a string pendulum even, is going more quickly now. That's what the omega does. So let me set that back at its original value of 1. And then I have a slider for the phase shift now. So this function can be phase shifted anywhere we want for any need. Now here's probably the biggest need for a phase shift. If we assume at t equals 0 that an object in SHM is at its max amplitude, then we would write this function with no phase shift. Okay, so let's imagine a spring pendulum bouncing up and down. As a matter of fact, let's get a spring pendulum. To show you guys. Bear with me here 1 second. Should have had this up already. Okay, here's a spring pendulum vertically that I'm going to start. So let's imagine that you can see they have a nice pattern here back and forth. So as time goes on, it just oscillates between its maximum height here to its minimum height down here. As long as there's no damping or effects of friction or anything like that, outside forces, this will go back and forth forever between the maximum and amplitude. But the thing is, on rating the position time function of it, at t equals 0, it doesn't have to start at the max amplitude. I could start a stopwatch timing the motion at any position. So when I start the stopwatch, maybe the object is at its equilibrium position, halfway between the min and max, which would be 0. So in that case, I could phase shift this one way or another. And right now at t equals 0, if we look at the black function compared to maybe the original cosine function, it's the same graph, but it's been phase shifted. It's been phase shifted positive 1.6 radians. And this represents at t equals 0, it was just at the equilibrium position, then oscillating. Or maybe we were at the lowest position. So I could phase shift one way or another at the min amplitude. Now that looks like the completely flipped around graph compared to it. Or in other words, it looks more like a negative cosine function. But it's not written that way. It could be, but it's done with a phase shift instead. So we could see that it starts down here. So the phase shift main point is you could write a cosine function like a sine function or vice versa. And all that really does is change what position you are on the graph at time t equals 0. And we often do that. I'm not going to spend much time on this, but I did write some graphs for the other ones. This is a similar function to what a velocity time graph would be. In a similar way, if we only change p the phase shift, it would move it right or left. And I also wrote one for the acceleration time function, which is a little messier looking, but it's the same idea. So just because of the derivation, some omegas are out front. In this case, the omega squared, but I can make it look however I want through the phase shift.